Welcome to CS50 Week 5 on data structures. My name is Kelly. I'm the preceptor here at Harvard, and I'm excited to be leading this section with you guys. Okay, so this week, some of the things we talked about are data structures, what kinds of data structures we can use, and some of the questions that might have come up for you from lecture might include, what are the key trade-offs between data structures that we should consider in decisions about which to use? What are some of the primary operations we should know how to do on a linked list, which is one of the data structures we learned about? And how can we build our very own hash table, which is another one of these data structures that we talked about. So to preface this first bit, we are going to talk about a lot of different data structures today, but we also want to try to get a sense of the intuition of when do we use each one and what kinds of things should we think about when we're choosing what data structure to use. So let's imagine this scenario where you work for a company that has created a digital assistant running on a mobile device. And so people have been indicating that some customers are having trouble activating this assistant with its wake word. So maybe you're trying to say hello, and then the assistant is supposed to wake up and start listening to the customer. So your team has been asked to ensure that this voice assistant can be awoken with a greater variety of words. So maybe instead of just listening for hello, you also want to listen for hi, or just low, or hello there. And so given this new variety of words that we want to capture, what data structure would you propose the team build to store these words? So as we talk about these data structures today, you can think about in the back of your mind, when you're making these kinds of decisions, what context are you thinking about and how might that help you choose a data structure? So one thing to keep in mind when choosing a data structure will be what you're going to actually be using this data structure for. What are the primary operations that are going to be used? And so some common ones could be deletion, insertion, and search. So in this case, deleting words from our list, inserting new words, and searching for words. And so with these operations that you might want to do, you also might have a prioritization for which ones are going to be used more often, and therefore which ones do we want to be faster. And so one way could be that we prioritize search. So we want the searching for a certain word to be really fast, or it could be that we're going to be inserting a lot of words very often, and so we want that to be faster. So it all depends on the context that you are working on. So one way that we could store these words is a linked list. So this is our first data structure. And so a linked list would look a little bit like this pictorially. We have some head to multiple nodes, and that these nodes are connected to each other. So let's say we're storing hello, hey, low there, and we could be storing more words like that. Another example we have here is a hash table. And so this hash table has multiple buckets, like in this case, these buckets are by the first letter. And then within the bucket, we have a linked list with multiple entries. Another data structure that we briefly heard about in lecture was a trie. And so this trie sort of has this tree-like structure that stores these words in a diagram sort of like this. Okay. So we've seen a couple of examples of data structures we can use. Now let's think about what trade-offs come with choosing one over the other. So in this week's problem set, Speller, we have this big board that tracks people's different algorithms based on their hash functions. And one thing to note here is that this is a past year's big board. We can see that the fastest implementation here also had the most memory. And so usually these two things, time and memory, time and space, are the big trade-offs you're going to be thinking about. So you could have something be really fast, but the downside might be that it's going to take up a lot of space. And on the opposite side, you could have something that takes up less space, but it might take a little bit longer. And so that's going to be a big trade-off that you're going to be thinking about when we're dealing with problems like this. Okay. So to start off, let's begin with talking about a linked list and what that looks like and how to create one for yourself. Okay. So the basis of a linked list is that we're going to be connecting a bunch of nodes, we call them. And so what actually is a node? So we're going to define a node like a struct, using a struct. And within this node, in this case, where we're trying to store a bunch of different words like hi, hello, we're going to store a phrase, which is a string. And then we're also going to store a pointer to the next node. So this is a pointer to something of a node type. And this address is going to be the address of the node that we'd like it to connect to. So this defines us a node type. We're storing some sort of phrase here, like hi. And then we're also storing what might be the address of the next node. Okay, so how do we go about creating a linked list? So we've created a node. How do we make this a list? So to start out with, we might have this list called list. And basically, we have a pointer to a node. And currently, it's just going to equal null. We haven't created any nodes yet. And so it's just going to equal, it's going to point to null for now. And then what we want to do here is actually malloc a node. So we're going to ask the computer for however much space a node needs and malloc that, and that's going to return the address of whatever memory was just malloced. Then we're creating some pointer called n here, and that n is going to point to that new piece of memory that we just allocated. So using our struct notation, I can then give it the phrase hi, which is, we know, a string. And then what do we think the next value should be? What address should it point to if this is the only thing in my list so far? Any ideas? Feel free to put in the chat. If this is my only node in the list so far, what should that next address point to? Yeah, so it would be the next address. But if I don't have another node, then exactly it should be pointing to null. So this indicates that my list is only this one node long and that there's no node that comes after my n node. So then I'm gonna reassign list to n so that this is now the head of my list. So I have list, which is a pointer, pointing to the head of my list. Okay, so I'll pause here if we have any questions about creating a linked list, what a node is, etc. So someone asked, what is a node? So we defined a node here with this notation here. So it's a struct that we've called node. And within the node, we're storing a phrase, which is a string, and then an address to a node, which is called next. Okay. Any other questions so far? Okay. Well, if any come up, feel free to put them in. And so we're going to get some hands-on practice with this and create a program called list.c that creates a linked list of 3 numbers. So in this example, we're going to be using numbers that are stored as a linked list, and we're going to define a struct called node, similar to what we just saw, which stores an integer and a pointer to the next node. In the main function, we're going to prompt the user for 3 numbers and dynamically allocate memory for each new node. Okay, so we're going to move here to CS50.dev. Okay, go. Okay, I'm just going to restart my code space. One second. Okay. Okay, I think we're set up now. Okay, I'm going to close this. Oops. Okay, we're all set. So I'm going to first start out by just including some libraries. So I know I'm going to get some input from the user, so I'm going to include CS50.h. And then what are some other libraries that I know I'm going to need here? Feel free to just write them in the chat. Yeah, definitely need standard io.h, so I'm going to include that. And then I'm also going to need standard lib, exactly. Great. Okay, and so my first point here, I need to know what a node is. So I'm going to have to define a node similar to what we just saw earlier. So I'm going to use my typedef struct notation to create what we're calling a node here. And then what were the things I wanted to include inside of my node? In the example we talked about, we had a string that we were saving, but in this case we want to save some numbers instead. Yeah, so I'm definitely going to need a pointer to the next node. But then I also want, instead of a phrase, an integer. I'm just going to call a number. And then I also want a pointer to the next node. So I'm going to call that next. Okay, great. And so now I'm going to set up my main function. All right. So I know that I'm going to be getting input 3 times. I also know I want to set up my linked list. So first, I'm just going to create that initial list pointer that points to the head of my list. And so list is going to be referring to the head of my list, no matter what I do to it. And for now, I'm just going to set that to null. Since I haven't allocated any nodes yet, it's just going to be empty. Okay. Now, how should I go about getting 3 numbers inputted from the user? Any ideas? I could do like number 1, get in, number 2. But is this the most efficient implementation? Yeah. So I should use a loop. I know I'm going to do it 3 times, so I'm going to say I less than 3, plus plus. So we're going to loop 3 times, and each time I'm going to get a new integer. Let's just call it x, using getInt. I'm going to ask for a new number. Okay. Now, once I have gotten this number, how do I go about creating a node for it. So what do I need to do when I create a new node? I know it's going to be node star. Yeah, and I'm going to malloc. So I'm going to need new memory to store this node in. So I'm going to call this n, and I'm going to use malloc to get the size of a node, so this amount of space from the computer. Okay. That's all good. And then if we recall from lecture, what do I always need to do when I malloc? So yeah, someone says check for null. Yeah, so when I ask for a certain amount of memory, this is going to return to me a pointer of where that memory lives. But in the case that the computer maybe doesn't have enough memory to give me, it's just going to return null. So it might be good to check here. If n is null, and in this case, I should just like stop the program, because the program is not going to go the way that I want it to, because I don't have enough space here. So I can return 1, and maybe I can just printf some sort of error here, like malloc failed. Okay, great. Any initial questions about this? We've defined a node here. We're looping 3 times and creating 3 nodes. Yeah, someone asks, does the number 3 here in the for loop, is that a magic number, or is it fine to hard code that? Yeah, that's a great question, and this is a really good like design question as well. Normally, I would say that when you're using these numbers that seem sort of arbitrary, it's better to define that as a constant. Since this is just a quick example, I'm not going to do that, but that's great intuition for completing the problem sets. Someone says, what if the error was in the middle of the for with the already allocated memory? Yeah, that's a great point. And so, yeah, what we might actually want to do is remove this for now and leave the freeing for later down in the function so that we know where to free. But yeah, that's a great question. Okay, so we're going to talk now about inserting nodes to a linked list. Right now we just have some floating nodes, but we don't have it actually linked together. So once we've created this new node, so let's say we're creating a second node here called n, and then we give it a phrase, and then to link it now, we've set the next pointer to our head of the list, which is called list. And then once that next value is set to the next node, that means I can reassign the head of the list, which is n, to this newly allocated node, which is now the head. Okay. So now let's do that in practice. Okay. So I've created a node here. And now I should probably give it the number that I actually got from the user here, right? So I'm going to do n number, set that equal to x. And then the next value should be what here? Yeah, list. And so for the first node, when list is null, that also makes sense here, since we're just going to insert this new node and set that next pointer. Okay, great. And then what do I have to do to reset the head of the list to the pointer, or to the node that we just created? So I should set list equal to n. Yeah, exactly. Exactly. So here we've created a new node called n. We've given it a number, we've set the next pointer. And then here we can reassign this head of the list to that node that we just created. Okay, great. Okay, so after we've set that up, we need to talk about freeing nodes, right? So we talked about when you malloc something, you always need to also free that memory afterwards. And so how do we do that? So naively, maybe I try this method, but what is wrong with freeing just list here? Right, so this other node hasn't been freed, and it's also not accessible anymore, since this node that we just freed had the pointer that was pointing to this node. And so basically what we've done here is just orphaned that node. So what do we want to do instead? So instead what we might consider is creating a pointer called PTR here, pointer, and we're going to set that to list next. And so now the address of that second node that before I orphaned, I'm saving this in a temporary pointer. So now I can free list, and I still have pointer pointing to the next node. And so I can reset list to pointer. So now it's at that new node. And again, I can reset pointer to the new next pointer. In this case, since we're at the end of the list, it's just equal to null. But then I can free list. Pointer is equal to null, which means I'm at the end of my list. And now everything has been freed, and we won't have any memory issues. Okay. So now we're going to implement this into the program that we're working on to extend list to traverse the linked list and print each number. And then we're going to free each node. Okay. So this code has now created a linked list of 3 numbers that were given to us by the user. And so now I'm going to try to print all of my nodes. So I know I'm going to use some sort of loop to go through each one. And then instead of a int I less than 3 here, what might I do to start with like the head of my list and go node by node? So I can start with a node called pointer. And I'm going to set that to the beginning of my list here, which is list, right? And then, so this method that we're working on here is slightly different to what I just showed you, but it has the same ideas of traversing the list one by one and also making sure that we're keeping track. So if we're going one by one and we're printing, I'm going to keep looping until my pointer is what? what indicates the end of my list? Yeah, null. So as long as this doesn't equal null, then I can keep looping. Okay. And then each time this iterates, I want to go to, my pointer should be going to the next node. Okay. So now this for loop will go one by one through the linked list until I reach the end. And so for each node, I also want to print out the number that I associated with it. So how do I get that number from the pointer that I'm on? So if I'm on the first, then I want to get the number that the user gave us. Yeah, so I'm going to do pointer number to get that number. Okay. Great. And so now this prints out our nodes, but we also want to remember to free those nodes as well. Okay. So similar to what we saw just now, I do want to create some sort of temporary pointer variable. Since this one was just within my for loop, I'm going to create a new one here that is outside of that scope. And I'm also going to set up a while loop to keep looping until I get to the end of my list. So what should my pointer be set to initially? Yeah, we can start it at list, right? And then what should the condition be within this while loop? How long should I be looping for? Yeah, so as long as this pointer does not equal null, then that means we haven't reached the end of the list yet. Okay. And so, like we saw earlier, I need some sort of variable that tracks the next node that I'm on so that I don't just free the one I'm on and orphan the rest of the list. So I'm going to create a temporary variable here. And what should it initially be set to here? Or in fact, I guess this pointer will be the one that will be going through, but then this temporary variable will hold the variable that I'm currently on. We could do it both ways here. So I could set it to pointer and then move pointer to pointer next, right? So this way, we're saving this value of pointer in our temporary node, and then we're moving pointer. You could also do it the other way around, where you move temporary variable to the next one, and then free pointer, but we're going to do it this way. And then which variable here am I freeing? So some people are saying pointer. If I freed pointer, which is now set to pointer next, then that would be freeing that next one, but not the one I'm currently on, and also not the ones beyond that. So it should be exactly like some people are saying, freeing temp. So that frees the node that I'm currently on, and then I have pointer pointing to the next node, so that when this loop runs again, and if I have still some of the list to go to, then pointer will now point to that next node, and I will now have this temporary node set to pointer. I'm going to update pointer to the next one, and then free temporary. Okay. So why don't we try this out and make sure it compiles. Oops. Okay, so I'm going to make list. Silly mistake here. Okay. So it's going to ask me for 3 numbers. I'm going to say 1, 2, 3, and then it prints them out. And does anyone know why it's printing them out 3, 2, 1, and not 1, 2, 3? Why is that happening? Yeah, someone said Philo, first in, last out. So because of the way that we set this up, right, where we've added 1 first, we've created 1 to be set into a node, and then when we create 2, we've made 2 the next head of the list. And then when we get 3, the same thing, we create a node for 3, and that sets 3 to be the head of the list. And so when we're printing this out and we're starting at the head, it's going to print out 3, then 2, then 1. Okay, great. Any questions about anything about this program? Okay. Okay. So building on this understanding of linked lists, now we're going to talk a bit about hash tables. So a linked list, like so, stores our values in like one long list. And what might be some like advantages of this and what might be some disadvantages? For example, how long might it take for me to search for a certain value in my linked list? Yeah, so people are saying it's better in memory, but it's O of n. So what does that mean? It means that if I'm searching for something, I might have to go through and look at each value in my linked list before I find that thing. And so it has an O of n runtime. And so can we do better than that is the question here. And hash table is another way of storing these values. A hash table is basically an array, and in each array is a new linked list. And so this hash table here that we've created is bucketizing, so like splitting up our entries based on a certain rule. So given a certain phrase like hey or hello, I'm going to give you a certain bucket that should go into. So in this case, our rule is just based on the first letter. So anything that starts with an H is going to stay in that H bucket, and it's going to be its own linked list separate from, say, low there, which will be in this L bucket. And so this sort of has the same trade-offs here. Now we're taking up a lot more memory because we have a new bucket for every single letter of the alphabet, even if they're not all going to be used. But it is going to be a little bit faster, since if I know the word I'm searching for starts with an H, I don't have to look at all the other buckets. I can just check the H bucket. Okay. And so each bucket also has a certain index, and that's where our hash function comes in. It basically will just map some input. So say we're looking for hey, it's going to input that into our hash function, and our hash function will return us the index of that bucket. So in this case, 7. Okay. So what if we tried a different hash function? So a different way of mapping our entries to buckets. So what might the mapping be in this case here? You can see the pattern. How are these 3 words mapped to buckets? yeah, the length, quantity of numbers, exactly. So in this case, we've defined our hash function to be whatever the length of our string is. So in this case, if I'm given hey exclamation point, then the hash function will be returning 4 as the length. And so a good hash function has certain properties. It's always going to give you the same value for the same input. So if I give it hey, the hash function should always give me the same value, and that should not change. It also will hopefully produce an even distribution across the buckets. So every bucket should be more or less the same length. And then we should also try to use all of the buckets. And so given those features, are the two examples that we just showed you good hash functions by those metrics? And why, if not? Yeah, so some people are saying no. Yeah, so some people are saying collisions, empty buckets. So if we looked at this initial hash function here that maps based on the first letter, it could be that some words just don't start with the letter Z, and then that bucket is empty. And we also might have an uneven distribution across these buckets, right? So we might have more words in the H category than we do in other categories. In this one here as well, it could be that we only have words of a certain length and we don't really have any more that are longer than that. And it could be also that most words are probably going to be within a certain amount of characters. And so we're going to have a lot of collisions, which basically just means we're going to have multiple entries mapped to the same hash bucket. But a good hash function would ideally only have a very short list, or if not just one value in each bucket, yeah. Okay, so any questions about hash functions? Okay, so now we're going to try to create our own hash function. Just see what that looks like in code. So if you're watching this at home, I encourage you to pause here and try it for yourself, but we're going to walk through it together here. So create a function or a program hash.c where we will complete a hash function to return a number between 0 and 25, depending on the first character in the word. And as we just talked about, this hash function is not a great hash function, and so we might try to find a way that we can improve this hash function. Okay, so I'm going to code hash.c here, and I'm going to include some libraries. standard.io.h, and then if there are more that we need, we'll come back. But I'm going to create my main function here. Oops. And just to test our hash function, let's create a string that we get from the user. So word. And then we'll print out the hash value. Okay. And we're going to make some function called hash here that I haven't defined yet that takes in a string. Okay. So let's create this hash function. So what is my input to a hash function? Yeah, string. Yeah, and someone says, yeah, like we learned last week, string is really just a char star. So I can just update that here and use char star word. And it's going to take in this word, and it's going to return to us some integer. And we know we're hoping for it to be between 0 and 25 based on its first letter. Okay. So what might we do to try to get that first letter from the string? Yeah, so we're trying to do something with its ASCII value. So how might, for example, a capital A map to 0? Okay, yeah, so we can do some like arithmetic. Someone says 2 upper the first character. Yeah, so that might be a good idea so the word we might get could be lowercase and it could be uppercase. And based on that, that also changes its ASCII value. So with A, for example, if I was given a lowercase a, then that would have the value 97. Whereas if I'm given an uppercase A, that's going to be 65. And so the arithmetic that we do there would be different. And so we could just say, like, if it's uppercase, then do this conversion. If it's lowercase, do this conversion. Another way we can do it here is to simply get that first character, let's say call it C, and just use the 2 upper function, which I should include here, is in the C type library. So I'm going to 2 upper the first character, which is going to be the 0th index of word. Okay, so once I know that this is uppercase, then I can do a conversion here and return, say, C minus uppercase A. So if this is, in fact, A, which would mean it has the value 65, if I subtract also the value 65, that'll give me 0, which will give that mapping of A to 0, B to 1, C to 2, etc., and etc. Okay, what are some issues with this function? Are there any cases that I might be forgetting about? Is there some way this could crash and everything would go wrong? So numbers, yeah, what if we are given a number as the first character? Yeah, sure. So that could be one thing. So maybe we should check before we do this conversion and return this, is my first character or maybe I'll do this after I 2 upper it. Yeah, is it alphabetical? I could do is alpha C. If it is, then great. Let's return its conversion. Yeah, so I could also put this here and then use word again here, but to avoid avoid using this twice, maybe I just first define char C as this first character, and then I can use C here. Here I convert this to uppercase, and then return. Okay, so we caught this case that it's not alphabetical. If it's not alphabetical, maybe we should just return, say, 0 as well. Or we could say like 26 or something like that. That would all be up to the design of your hash function. Let's just say we return 0. Are there any other edge cases that I might be failing to account for? That's true. This would hash to the same as A characters. So we could also say -1 maybe. Someone asked, do we need an else here? Since we return at the end of this within the if, having an else here would not change the logical flow. So, okay, well, let me propose, what if this char star word doesn't have a first character? So if my word was not, like I wasn't given anything, I just got a string with null, the null character, then I should also probably account for that, because otherwise if I try to index into the first character, that's going to cause some issues. So maybe I'm going to check if the word is null, or you could say if the length of the word is 0, then let's return also -1 maybe. Okay. Yeah, we're asking if there's a space before. Yeah, so this would be up to the design of your hash function. If you wanted to ignore white space before a word, you could do that. In this case, we can just be really simple about it and just take that first character. If it's a space, that means it's not an alphabetical character, and just return -1. So let's try this now. What errors came up here? Oh. Okay. Ah. What's the error here? Called undeclared function hash. What did I forget to do? Prototype. Yeah, so I need to define it up here before I use it. And I also forgot to include string.h. So let's do that. All right, no errors this time. I run /hash and I give it the word, say, cat, then hopefully this should give us 2. There we go. What if I give it nothing? I just press enter, hash value of -1, like we defined here. I could even say maybe if it's empty, I just return -2. If I do /hash, I give it nothing, then it gives us -2. If I do /hash with a non-alphabetical word here, then we have -1. So we kind of have differentiated these two cases here. And of course, for uppercase and lowercase, cat should give us 2. Okay. Any questions about this hash function? Someone asks if there is a string method to check for spaces. Yeah, you can use isSpace to check if something is a space. Someone suggested the dot strip in Python, but yeah, that is a Python-specific function. Okay. Okay, so we have this hash function, but like we said before, it's maybe not great at being a good hash function. And so what might be some small improvements we can make here to make this hash function a little bit better? So if we had a bunch of words, say in like the H bucket, what would be a way of turning that into multiple buckets rather than just one H bucket? So like, yeah, we want to introduce more buckets, but with more buckets, we need some sort of mapping to those buckets. So one way we could do it is maybe instead of just mapping by the first letter, yeah, we map by 2 letters maybe. Okay, so how would we update this now? Well, we should probably catch the case that this is not 2 letters long. So if the string length of the word is, say, less than 2, then we should catch that. Okay. Otherwise, how might I return some sort of value based on its first 2 letters? What if the word is just A? Yeah, exactly. So if it's not long enough, then we can catch that. Yeah, we could do some sort of addition, maybe. Although, let's say if we took, this is the first character and then the second character, and we check that they're both alphabetical, and then we uppercase both of them. If we added these values together, like so, would this have a unique bucket for every 2-letter combination? Someone says no. Why is that? So if I had a word that started with, say, AC, that would be A is corresponding with 0, C would correspond with 2. I could also have something like B and B. That would give us the same bucket. Yeah, so that would cause a collision. Yeah, so someone is proposing we do this first letter's value, multiply that by 100, and then give us, and then add the second letter. So using this, that would mean something starting with the letters AC would map to 2, and BB would map to 101 instead of also 2. So yeah, these are some techniques that we can use to differentiate the buckets of our inputs. And so there are a lot of different ways of doing this. You could even, instead of looking at the first 2, maybe you take the sum of all of the ASCII characters of our thing. Yeah, you could do, someone's proposing if we do C plus C1 minus A. This might have the same issue that we just had where we have some collisions, even if they're different values. But yeah, so these are some things you can think about as you're working on Speller this week, since you will also be implementing your own hash function, and hopefully your hash function will be better than this one or the one that we first created where we just mapped by the first letter. But continue this line of thinking to keep thinking about how can we make these buckets more even, better distributed, and thus making our search faster. Okay. So with that, that's CS50 week 5 on data structures. And we hope you come back next week for week 6, where we'll be leaving C and moving to Python. Okay, see you there.